Welcome to the Deep Dive. Today we are taking a fascinating plunge into some of the most cutting-edge research in artificial intelligence. We're talking about the world of truly autonomous agents, the ones powered by large language models. These are the systems that promise to reason, to use multiple tools, everything from coding interfaces to web browsers, and to execute these really complex multi-step tasks without constant human guidance.
Right.
The goal, ultimately, is a massive boost to human productivity. But if you followed this field, you know that despite this incredible promise, current training methods
Yeah.
for these sophisticated agents, they often just hit a wall of staggering cost and inefficiency. We just rely way too much on manual labor to hold the agent's hand.
That's absolutely right. And the source material we're digging into today addresses this head on with a new framework they're calling AgentEvolver.
AgentEvolver.
Yes, and it's a self-evolving system designed to transfer the burden of learning, entirely to the LLM itself. When we look at why reinforcement learning agents struggle today, we see three critical roadblocks the system is built to remove.
Okay.
First, there's the high cost and just the scarcity of diverse task datasets. Training an agent to use, say, 10 different APIs requires humans to manually craft thousands of relevant scenarios.
Because that's just...
It's just slow, expensive work. Second, traditional training methods are highly inefficient. They rely on what's essentially approximate brute force exploration.
So you're saying it's like asking a student to learn calculus by just randomly guessing answers until they stumble upon the right one.
Exactly, just throwing spaghetti at the wall. And the third problem is feedback. Even when the agent succeeds in that complex multi-step environment, it only gets a sparse single reward at the very end.
The classic credit assignment problem.
Yeah, right. If the task took 100 steps, how does the agent know which 5 steps were brilliant and which 5 were, catastrophic? That means poor utilization of the samples it does generate.
So our mission for this deep dive is to unpack AgentEvolver, which proposes this seamless self-training loop to solve these three problems all at once. It achieves this by implementing three key synergistic mechanisms: self-questioning, self-navigating, and self-attributing. We're going to explore how these allow the LLM to drive its own learning process from start to finish.
Let's focus on that first hurdle: task scarcity. Think about an agent dropped into a totally novel environment, maybe one with a new set of developer tools or an unfamiliar operating system.
Right.
Manually constructing a rich, multi-step training curriculum that covers all possible tool interactions is, well, that's nearly impossible.
It is so much.
You end up with training data that is low quality, lacks diversity, and ultimately it just constrains the agent's general capabilities.
Okay, let's unpack the core idea here. The architecture separates the world into two parts. You have the interaction sandbox,
Yeah.
the actual environment with its states and actions, but no built-in goals or rewards. And then you have the external unknown tasks the agent should be able to solve eventually. The radical idea of AgentEvolver is that the agent has to force itself to generate its own training objectives within that sandbox.
That's the intellectual leap. Traditional methods, things based on PPO, they rely on generating massive volumes of redundant trajectory samples.
Which is so expensive.
It's computationally heavy and financially expensive, especially for these long horizon tasks. AgentEvolver says, stop the brute force sampling and start asking smart questions.
This raises an important question. If the environment gives the agent no intrinsic goals, how do you make it curious enough to generate challenging yet solvable homework assignments for itself?
That is precisely what Mechanism 1's self-questioning achieves. It replaces the costly human curriculum designer. It uses something called curiosity-guided exploration, which is a lot more sophisticated than just random actions.
How so?
First, the agent has to build a map. It uses environment profiles, which are summaries of the entities, attributes, and operations available.
So if it's a virtual world, it maps out the locations. If it's a coding environment, it identifies the functions.
Exactly. This prevents the agent from just aimlessly wandering.
So it's like giving a toddler a list of all the toys in the room before you tell them to play. They know the scope of their world.
A perfect analogy. Then, to stimulate creativity, they use a high-temperature LLM as the source of curiosity.
High temperature meaning more random, more creative outputs.
Right. That elevated temperature encourages diverse, unconventional action patterns. It pushes the agent out of its comfort zone to discover hidden states and unexpected functionality.
Interesting.
They even split this exploration, an initial broad strokes phase for basic understanding, followed by a depth-first dive, where the agent limits its focus to only recent steps.
To keep it from getting stuck on one long path forever.
Exactly.
Here's where it gets really interesting for me. Once the agent performs a successful, if accidental path, say it figures out how to open a menu and save a file, how does it turn that raw path into a viable, repeatable assignment for its future self?
That's adaptive task synthesis. The explored trajectory is distilled down to its core components. The agent then combines that successful path with a desired user criteria like, make this task require at least 3 different operations.
Oh, so you can guide the difficulty.
You can. And it synthesizes a clear task query, a goal. The successful path itself is condensed into a reference solution. That becomes the proxy ground truth.
But wait, if the exploration is high temperature and creative, how do they ensure the agent doesn't spend all its time exploring dead ends or, worse, hallucinating impossible tasks? I mean, if the LLM generates the task, it could potentially make up an invalid one.
That is solved by rigorous task curation.
Okay.
First, they deduplicate tasks in real time to avoid repetition. But more critically, they perform a feasibility assessment after synthesis,
Right.
a check. They use that reference solution that generated the task to strictly verify its executability. If the reference path confirms the task can be done, it's a viable assignment.
And if not?
It's discarded. This process is absolutely critical for removing those hallucinatory tasks generated during high-temperature exploration.
And finally, that LLM judge provides the synthetic task reward. It doesn't just say pass or fail when the agent attempts the task later.
No, it's much smarter than that.
It uses a reference-based correctness check to compare the agent's steps against the known optimal solution, offering nuanced, continuous scoring.
Right. Correct solutions get high scores, even if they're imperfect, and incorrect ones get low scores. This rich signal is already a vast improvement over standard binary metrics.
It truly is.
Which brings us to mechanism 2, self-navigating.
Okay.
Once the agent has generated a massive library of its own training tasks, the next logical hurdle is making sure it tackles them intelligently, not with that random trial and error.
So if traditional RL is like throwing spaghetti at the wall,
Self-navigating aims for human-like learning, systematically applying past lessons to guide future attempts.
so this is all about improving exploration efficiency by remembering what worked and what didn't.
Precisely. They create experiences-structured knowledge distilled from past, highly successful trajectories, all articulated in natural language.
So it's not just a stored trajectory.
No, it's a piece of wisdom. It has 2 parts. The when to use trigger, like if you encounter an error when loading an object, and the content, which is the instruction, such as always check the environment logs before retrying the action.
And this experience informs the rollout.
It informs the experience mixed rollout. The system balances pure exploration, the vanilla rollouts, with experience-guided rollouts.
Okay.
And crucially, they found that relying too heavily on prior knowledge can actually constrain long-term optimization.
It stops the agent from finding novel, maybe even better solutions.
Yes. So they maintain a balance, mixing both methods to prevent excessive conservatism.
That makes intuitive sense. If you rely on old tricks too much, you never discover new ones. But I see a potential problem here. If you inject the experience, this instruction, always check the logs, into the agent's prompt to guide its action, you're basically giving it the answer key.
Right.
How do you prevent the model from just memorizing the literal prompt and not truly learning the underlying principle?
That's where 2 brilliant techniques come into play. The first is experience stripping.
Stripping.
Before they compute the policy gradient, the actual learning step, they literally remove the guiding experience prompt from the sample.
So it's like a student who studies with flashcards. They can ace the test if the answer's on the back.
The prompt.
But if you want them to internalize the concept, you have to strip the answer away before the long-term learning happens.
Exactly. However, stripping the prompt creates an inference and learning mismatch, which can destabilize the training.
Because the agent acted well because of the experience, but now it's being optimized without that context.
You've got it. This leads to the second technique, selective boosting.
Selective boosting. What's the core insight here?
The insight is this. If a trajectory was experience-guided and yielded a genuinely positive advantage, meaning it was a good outcome, the system decides to learn more aggressively from it.
So it prioritizes those samples.
It does. For these favorable samples, they relax the typical safety controls used in optimization that normally prevent big, fast learning steps. They allow a larger adjustment of the policy to preserve and lock in the optimization signals from that good, experience-conditioned behavior.
That's a fundamentally different approach.
Hmm.
Instead of treating every sample the same, they amplify the value of the best learning opportunities.
Precisely. Which brings us to mechanism 3, self-attributing. This mechanism tackles the last but perhaps most debilitating problem, that sparse trajectory-level reward.
Right, the credit assignment problem. You have 100 steps in a complex task, and you only get a single reward at the very end.
Yeah.
How do you tell the agent which step made the difference?
You can't, not easily.
So self-attributing turns that single outcome reward into a dense, stepwise signal.
We can use the analogy of a football coach reviewing game film. The final score might have been a loss, a low terminal reward, but the coach can still review the film and assign credit or blame step by step. That's stepwise attribution.
So an LLM judge plays the coach.
Exactly. It retrospectively analyzes the entire trajectory using a specialized, detailed prompt to categorize every single step as either good or bad based on its contribution to the overall outcome.
And this allows for what they call composite reward construction.
Yes, they create two independently normalized reward channels. Channel 1 is process quality, derived directly from those good-bad labels, essentially giving a +1 for a good step and a -1 for a bad one.
And channel 2?
Channel 2 is outcome effectiveness, which is just the final terminal reward.
And then they fuse them into a single stepwise learning signal. The hyperparameter that controls how much weight is given to the process quality, the step-by-step praise or critique, versus the final outcome effectiveness is called the guidance weight.
That guidance weight is where the critical trade-off lies. Studies show that if they set the weight too high, if they prioritize the judge's process feedback too much, it accelerated early learning dramatically.
But there was a cost?
There was a cost.
Yeah.
It hurt long-term generalization.
Is that because the agent was essentially learning to please the LLM judge's heuristics, the process, rather than mastering the actual task environment?
Exactly. It would overfit to the judge's internal style rules instead of focusing on actual success. The optimal guidance weight they found provided a balance.
A sweet spot.
Just enough fine-grained guidance to stabilize learning and improve sample efficiency without letting the agent forget that the ultimate goal is completing the task successfully.
And the practical payoff here is significant. This dense feedback enhances sample efficiency in a big way. The Quinn model, for example, require between 55 and 67% fewer training steps to reach 90% of the baseline system's performance on complex benchmarks.
That's huge.
They are learning faster, cheaper, and with so much less wasted effort.
Moving to the big picture results. The synergy of these three self-driven components really confirms the promise of AgentEvolver. The overall performance gains are dramatic.
What kind of numbers are we talking about?
Their smaller 7 billion parameter model saw its macro average success score jump from around 15% using a vanilla training approach to over 45% when using the complete AgentEvolver system.
That's a threefold increase in capability simply by changing how the agent learns. Before we wrap up, we have to mention one architectural component that facilitates all this complexity, the context manager.
The context manager is crucial because these are multi-turn interactions and memory is everything. In long tasks, the agent has a limited memory, a token budget.
Right.
And the research highlighted that the most effective approach was the self-context managing template, or SCMT.
This is truly meta-autonomy, isn't it? Instead of the human developer coding rules about when to compress memory, the agent policy itself is tasked with dynamically deciding when to preserve, delete, or summarize memory segments.
It is. By granting the agent control over its own token budget, they found it significantly improved focused reasoning, leading to the best performance.
Because the agent could focus on the immediate relevant context without getting lost in old chatter.
Precisely.
To summarize the core achievement of AgentEvolver, it successfully delegates the entire learning initiative, from task generation and exploration guidance to fine-grained, stepwise reward assessment to the LLM itself. It's moving us far beyond the manual, human-engineered training pipelines that have constrained scaling up until now.
We can concisely state how the bottlenecks fell. Task scarcity is solved by self-questioning.
Tech.
Exploration inefficiency is solved by self-navigating and reusing that structured knowledge.
Valid.
And low sample utilization is solved by self-attributing, which provides that dense instructional credit assignment.
That brings us to the final provocative thought, looking at the next steps in this research. The current AgentEvolver system still uses separate components for the LLM judge, the exploration policy, and the optimization policy.
It's a distributed brain, so to speak.
It is. What's truly fascinating is the next frontier. Unifying all these functions, task generation, experience abstraction, self-attribution, and inference, within a single, tightly coupled LLM. This raises an important question. What happens when the agent not only learns, but becomes the entire closed-loop scientific process for its own continual evolution, maintaining a self-consistent body of procedural knowledge without any external intervention at all?